Hi, everyone. Good morning. Welcome to today's Rubin Science Assembly. You should be hearing my voice, seeing my screen. Got a nod, thank you. Okay, I think we're good to go. Recording is on. My name's Melissa Graham. I'm the lead community scientist for Rubin Observatory. Strong lensing's not my science area, but I think we've prepared a pretty useful little tutorial for you here today. So we'll be doing our best. There are a bunch of community science team members and lots of people who know more about strong lensing than I here. So please feel free to use the Zoom chat to ask questions at any time while I'm talking. And then other people will be here to answer them for you. Like every Rubin Science Assembly, we're going to start with announcements, and there's going to be a short presentation on strong lensing with the LSST and the Rubin data products that are most relevant to strong lensing science. The focus of today's seminar is not to teach strong lensing astronomy, and it is not like all the kinds of strong lensing results expected for LSST, but rather the format and the access methods for the LSST data products so that you're ready for the first real data release of the year. While I'm talking, I'm going to put some links in the chat for you. They're the links to this slide deck. It's the link to the GitHub repo that we'll be using today, and it's the exact statement, the exact git clone statement that you put into a terminal in order to get the tutorials that we're going to do today in the Rubin Science platform. So if you're not new, you've used the Rubin Science platform and Git before, the brief instructions for you, like in one browser tab, go into the portal, in another browser tab, go into the notebook aspect and git clone today's repo. You'll be good to go. If you're completely new to the Rubin Science platform and maybe have never used Git before, these step-by-step instructions are something. Take a screenshot, open the slides for yourself, get yourself set up while I'm going through the presentation part, and you'll be ready when we get to the tutorial portion. All right, if you're new here, here's another really handy slide with a bunch of links of how to get a Rubin Science platform account, where to find our data products documentation, general information for scientists. Our community forum at community.lsst.org is where to go to ask questions and get help. And if you want to learn more in general about Rubin Early Science and the path to Data Preview 1, the first release of real data, there's some links there for you as well. For announcements, the Rubin Community Workshop 2025 is going to start on July 28th. It's going to be in Tucson. It will be fully hybrid, and the registration and abstract submission are now open. The website is linked there. For the upcoming Rubin Science Assemblies, we're in week 2 of our science prep series on strong. This week is strong lensing. Next week will be galaxies, and in 2 weeks' time will be time domain, and so on. The third announcement is that there is a call for input on community filters for the Antares alert broker. Everyone is welcome to submit to this call. It's very informal. The deadline is May 30th, but this is only the first round of input. We're just looking for general science use cases that you have for an alert broker like Antares, because as a team, we want to set up a couple of workhorse filters that will serve a broad section of the community. So you don't need to write a filter. This isn't looking for code. This is looking for short descriptions of science use cases, things you would like to be able to do with the alert broker, and that'll help us. For more information on that, there's a community forum link there to look at that call. The other great news, of course, is that the LSST science camera has been installed on the telescope. That was a couple of weeks ago. Here's Brian on the platform looking at the installed camera. And there's a lot more description and lots of really pretty pictures at this link right here. As always, we want to mention that the Link Frameworks team also hosts a drop-in session that's right after our Rubin Science Assemblies, Thursdays at 10 a.m. Pacific. So you can drop in there if you want to learn about their software. Always too, I like to mention the users committee exists. Their next, they meet twice a year, and the next one is coming up at the end of April, but they're very open to hearing from you at any time about any aspect of the usability and scientific suitability of the Rubin Science platform and the data products. They have a Google form that they would just love to hear from you about how things are going. Do you feel prepared for science? That kind of thing. All right. That ends our announcements. Let's get started with a brief introduction to strong lensing science with the Rubin Observatory. Let's start with some pretty pictures. These are mostly from space telescopes, but they provide a very nice summary of how strong lenses appear as arcs, as rings, or as multiply imaged point sources. So very beautiful topic that we have today. This graphic demonstrates how strong lensing occurs when a foreground galaxy's mass perceptibly distorts the light from a background galaxy. So the foreground galaxy is blue, the background one is red. Um, and that makes it appear magnified and multiply imaged as an arc, a ring, or a set of blobs as in this demo, instead of its true shape and brightness. And for this image, like I left, it's a little bit more of a technical schematic of the angles and measurements of the source, which is in this case, before was the red, now it's the black circle at left. We've got the source, the lens, which is marked with an L in the center there, and then the observer over on the right-hand side marked with an O. So this is like very similar to the last graphic we just showed. It's just like a schematic diagram that also shows the apparent positions of the source marked as I1 and I2 over at left. And then it has the relevant measurable quantities, such as the distance between the source and lens, the distance between the lens and the observer, and the angles on the sky between the source, the lens, and the strongly lensed images of the source. All of these quantities, these measurable quantities, are all related to each other by the lens equation at right. For the particular case where a source is directly behind the lens and not slightly offset, as in the schematic, the Einstein equation, the Einstein radius equation applies. We're not going super deep into these equations today, only making the point that the observable measurements related to the physical parameter of the lens mass, m, which is the total mass, including dark matter of the lensing galaxy. So the observations of strong lensing allow for measurements of dark matter. Yeah, here we've got the measurements, the observable parameters in orange, and then the physical thing that you can derive from it underlined in green there. Due to the different path lengths for the light to travel from the source to the lens for I1 versus I2, a supernova, for example, will appear at different times in the multiple images of the source. And that time delay, that delta T AB in these equations, is another observable measurement, another like observable effect of strong lensing. And in this case, the time delay, it relates not just to the total mass of the lens, but also its mass distribution, like the profile of its mass on the sky, and it also relates to the Hubble constant. That's the two physical parameters that are underlined in green here that are related to the observable parameter of the time delay. So this is one way that strong lensing is used for cosmology. All right, that's your strong lensing 101 and how it relates to how you go from observable parameters to physical parameters. So the Legacy Survey of Space and Time, the LSST, will contribute to strong lensing studies primarily by its large volume of discovery and its multi-band time series coverage for time-domain events. The image at left shows the number of observations after 10 years in all 6 filters across the southern sky. High resolution is important for strong lensing studies, like as we saw in the very first image, all the pretty space telescope pictures. And the image quality is projected to be good, like a median of 0.7 arc seconds, full width half max seeing, with the very best images from the LSST having a seeing of around 0.4 arc seconds. The LSSD science book has this great plot of the predicted number of galaxy strong lenses that should be discoverable in LSST. The number expected is on the contour lines in this plot, where the y-axis is the seeing full width half max, and the x-axis is the surface brightness limit of the image, or the depth of the image. There are 2 markers on this plot. The orange plus sign shows the number of galaxy lenses discoverable in the best seeing single visit images. Those images are shallower, but since you have many of them, some of them are at the best seeing, so some of them have the much smaller full width half max. And so you can find a lot more lenses when you have that good seeing, that good image quality. The green asterisk, on the other hand, shows the number of galaxy-galaxy lenses discoverable in the deeply co-added images. They're deeper, obviously, since they're coads, but their full width half max is larger since they're a combination of all the images that we took. So they have that mean of 0.7 arc seconds. And so actually fewer galaxy lenses can be found in the deep coads due to having to stack and having a poorer um, image quality. But still, the point is that altogether, the expectation is about 10,000 discoverable galaxy lenses in the LSST footprint when you consider all the data taken all together. So I really like this plot from the science book. I found that pretty interesting. So that's what we're after. That's one estimate of what LSST will be able to do for strong lensing. As you might already know, there's a strong lensing science collaboration, and their members work together to prepare for LSST. It's not mandatory to join any science collaboration in order to do science with the Rubin data, but they are really great places to collaborate and to network. I'll note that the strong lensing is also an interest of the dark energy science collaboration. So there's some links on this slide if you're interested in looking into joining either of these science collaborations. They are accepting applications for new members. All right. Brief introduction to the LSST data products that everyone's going to be using to do all of this science that we just talked about. So today we're only going to focus on the data products that are relevant for static sky strong lensing analysis because everything about time domain is going to be covered on Thursday, April 10th. This is a single slide that summarizes all the LSST data products. The top two sort of rows here are more for time domain. So the relevant ones for the static sky strong lensing are across the bottom here, the annual data releases. These annual data releases include all the processed single visit images, plus the deeply co-added images, and catalogs of measurements made of every detection in every image in every filter. And these data products are made available via the Rubin Science platform, which is also what we're going to be using today for the hands-on tutorial part. For images, for either the processed single visit images or the deep coads, they're all fully processed and calibrated, and they are science ready and come fully loaded with metadata such as the WCS, the PSF, mask planes, and so on. For terminology, the single visit images are commonly called CalExps, and the deeply co-added images are usually just called deep coads. For catalogs, Rubin uses the term source for a detection in a single visit image and object for a detection in a deep coad. And here, detection in both cases means signal to noise ratio greater than 5. Detection, deblending, and measurement is done to create the source and object catalogs. These catalogs contain a wide variety of shape and photometry measurements and a whole bunch of flags to help you interpret these measurements. The force source catalog contains force photometry at the location of all objects, but done on all the single visit images. So every object that's detected in a deep coad, you also have access to force photometry over all time. So all of that will be there, will be available to you. You don't have to do any image, like no image reduction is necessary. You can just go straight to the catalogs. They're science ready, ready for you to do your science. So with that very brief introduction, we're pretty much ready to move into our hands-on tutorials. For today, we're using the simulated LSST-like data products called Data Preview 0. DP0 doesn't have any strongly lensed sources in it, like in the simulation or in the data. So we're gonna have to pretend, but that's okay. We're going to use the portal first to pretend to identify potential lenses and examine them in the deep coads. Then we're going to use the notebook aspect to inject images of known lens systems into a single visit image and then detect them and see what their detections and their measurements are like. So let's get to it. I am keeping an eye on the chat, and so far no questions have come through. But please don't feel like you need to hold back or hold your questions to the end. That's what the Zoom chat is for. All right, let's get you set up. So if we spin back to the instructions, it was to start in one browser tab, go to the URL data.lsst.cloud and enter the portal aspect. That should get you here to this landing page. So this is what you should be seeing in one of your browser tabs. The portal tutorial that we're going to work through is in that same GitHub repo that I had you git clone into the notebook aspect. In the chat, I just put the direct link to the portal tutorial that we're going to be working from first for the first tutorial. So you have that open. You can see I have them open side by side. My tutorial here, the portal aspect landing pages here. So I'm gonna get started on this first tutorial. So for this first one, I've taken the sort of science use case of let's just look for galaxies that might be lens sources. So galaxies that are like big, massive, lower redshift to mid redshift elliptical galaxies. That's all we're going to be looking for today. But the point here is to get you into the portal, touching some of the data. That's more the point than doing a very realistic strong lensing, strong lensing analysis. The point is more just to get you touching the data. So in this tutorial, I have provided like a bit of an introduction, just like we just went through, a little bit of a note about terminology and the fact that there's no strong lenses actually in the DP0. And I also want to make the point that this is not an introductory level tutorial. Neither of the things we're doing today are introductory level. If you're completely new to the RSP, there are a ton of other introductory level tutorials for you to learn step by step how to use the portal, how to use the notebooks, all that kind of thing. We're just sort of going straight into it. This is more of an intermediate to advanced level tutorial today. So that's just sort of a bit of a warning there. All right, step one, log into the RSP portal. That we've done. Step 1.2 is to navigate to the ADQL interface. So we're here, we're using DP0. We're going to be accessing DP0 catalogs. So I choose the DP0.2 catalogs. And the first thing I want you to notice is that from here is a really nice way to browse what all the DP0.2 catalogs are. So you can see here the object and source and force source, like I was just mentioning in the slides, they're all here. Right now, object is the default one. That's the detections and the coads. This is a nice way to browse all what is in the object catalog. You can see the name of every single column here. You can look for columns that are just hold some flux values. You can search the descriptions for the columns. For example, if I want to see all the columns that are related to centroids of objects that have been detected, you can type centroid in. So this is a really easy way to sort of browse the catalogs, understand the schema, learn about what's in there, that kind of thing. But today, so you can also set up queries from here. You can set your center coordinates. You can do a cone search. Over on this side, you can say, I only want to, return a couple of columns. You can put constraints on the columns over here, and then you could do a search from here. But I've already set up a query for us, and that is here in the tutorial. It's a query that will return the object ID, the coordinates, and the GR and I fluxes. And here we're using C model fluxes, which are appropriate for extended objects. We want to return those from the object catalog, and we want to return it for all objects that are within 1 degree of these central coordinates that I've defined. This is just a demo, so we just pick some coordinates. We want to look and see what's there. We're using the set detect as primary, which is always recommended to have that flag be true so that we're rejecting duplicates. We're setting the extendedness parameter to be equal to 1 because we're looking for galaxies today, not point sources. And then here I have a bunch of constraints on the flux values. I want to find big, massive, sort of lower redshift galaxies that are probably elliptical galaxies. So I want them to be bright. So I've set lower limits on the flux. And I want them to be red because I want to find potential elliptical galaxies. So I put on a constraint that the G flux is less than the R flux is less than the I flux. So all of this together, copy paste from here, and we can put this straight into the ADQL box and make this query on the object catalog. This should be pretty quick. Sometimes things do take a little longer when we're all doing the same thing at the same time, and that's fine. I'm keeping an eye on the Zoom chat for questions. Questions are also just if you have trouble accessing any of these resources. This is taking significantly longer than when I was doing it before. Of course, since it's a live demo. Joven, thank you for confirming your results came back in 10 seconds. That was closer. That's closer to the expectation. Yeah. That was taking a very long time. I'm going to use a different interface. See if I can get a faster response so that we don't get stuck here. And then if it really won't go for me, I'll just switch over to the notebook tutorial. But that's more like what's supposed to happen. Okay. We will continue in here. Right, except that all I'm having is problems today. This is not what's supposed to show on this side. Why are you being weird? Why is everything being weird? This is supposed to be a nice plot. Yeah. Yeah, Yumi, I think there should be like around 20 people doing the same thing at the same moment. But just last week, the RSP developer team successfully scale tested with 2,000 simultaneous users and it went fine. So I really did not expect to have problems with just 20 of us today. This problem of cannot display requested data is baffling. That's not supposed to be the way. Let me just sort of fully try again. Okay, this is what was supposed to happen. There we go, much nicer. All right, back in business. All right, so we've done our query. We've got a bunch of bright red galaxies. The portal automatically shows you the HIPS map at upper left here, with all of the objects returned by your query marked. At upper right, it shows you the plot that it automatically makes. It takes the first two columns and it plots them against each other. So in this case, declination versus right ascension. And then down at the bottom, it's got the table. Whatever object is selected shows up as orange, like in all three places. So you can use this to come in, browse the results that you just got. All right, great. So confirm results view, step 2.1, that is done. We've got our results, 104 galaxies matched our query. And now let's select an interesting object. All right, so you kind of take a look here and you can see there's clumpings of galaxies. So there's a clump over here. Oh, this looks pretty interesting. Um, Looks like there's lots of galaxies in here. Let's zoom in a bit. Yeah, lots of interesting galaxies in this area. You can pick one, for example, zoom all the way in. And whatever you've picked in any screen will show up in the others. Is it normal that I don't get the left panel displayed? Not normal, but there are two tabs at upper left, and it is the coverage map one that I'm showing. There are also ways to set your results layout to only have two of the given three possible panels. Yeah, so that might be what it is. You want to be in the try view. Okay, so we got a galaxy. We've zoomed in on a galaxy of interest. And you can pick any one, doesn't have to be the same one that I picked. You can browse around and then say you're browsing around and you're like, oh, that galaxy looks pretty interesting. And then step 3 of this tutorial is to view the same object, not in the HIPS map, which it is nice because it is a color, but you can see the resolution is not, the image resolution of the Rubin images. This is definitely a map that has been created for fast, quick browsing of the deeply co-added images. So let's go look at the actual deep co-add images in each of the filters for your object of interest. First thing is to select the object in the table. It's already highlighted as orange for us by the portal, which is great. So we're just going to select the little checkbox way over at left. And then we're going to use this icon, the search dropdown, where you can make additional searches on the Rubin data based on the object that you've selected in the table. And in this case, we want the deep co-add images. So we're going to come here and say, let's go and search the OBS tab for all the images that Rubin has for this given row. So we click on that, and it automatically takes us back to the search interface, but this time it's searching for images, and it has already put in the RA index of the object that we were interested in down here under the location search, and it has set up the table that we want to be querying for image metadata, etc. Since we want to take a look at the deep co-add image, it's calibration level 3 is what includes the deep co-adds. So we check box number 3. Everything else for now can be left empty, except that we do want the deep co-adds. And so the data product subtype for deep co-adds in this list is lsst.deepcoadd underscore calx, which is more about the format of the image. It's the fact that it's a deep co-add that we want. That takes us to, that is step 3.3 if you're following along. We've set up our query, and now we can click the search button at lower left. All right, and in this case, we can see that our query has returned it's returned to us 6 images, 6 deeply co-added images, 1 per filter that contain our object of interest. So the one that is being displayed right now is the Z band, because I can tell because it's highlighted. In the, we want to switch to R band. I just clicked on the row for the R band image. Now it's showing the R band. It's showing the similar sort of markings of the sources that from our first query as we were seeing in the coverage map. And now if we go back to the coverage map, we can see that the location of the image that we just retrieved is also marked on the coverage map. Very handy. So that's the HIPS map version. This is the actual deep coad version, and we can zoom in. The object that we had selected before is also marked in orange here. So now we have not the HIPS map version of our object of interest, which was, where did it go? Which was here. But we have the proper deep coad image. So you're getting a lot more information. And from here, within the portal, you have access to a lot of different image analysis tools, such as like extracting line plots. You can change the scaling, change the color map, all that kind of stuff. You can do it all in there. So that is the example workflow, starting from I want to find galaxies of interest. I want to look at them in the color image, the HIPS map color image, all the way through to I want to get the deep coad for that and take a closer look. So this is all very much browsing the data, taking, discovering objects of interest, that kind of thing. Can take a quick pause for questions on the portal. Just looking in the chat. All right. Continue to pop your questions in the chat if you have them, and we'll move on to how does the deep coad get to be a clean coad? Oh, like all the information about how deep coads are created, like how the stacking is done, that will be in algorithm papers eventually. I think that the answer to that is very long of how you stack images to make like nice clean coads. So I can't fully answer that today. That's a whole papers level stuff about stacking algorithms. All right. So if you followed the second set of instructions in a second browser tab, go to the URL data.lsst.cloud, enter the notebook aspect, and then you'll want to have git cloned this DP1 science prep seminars repo in, and you will have within that folder, there's a strong lensing subfolder. And in that strong lensing subfolder, there's an IPyMB file, a strong lensing demo injection and detection. So open that up, and this is what we're using for our notebook tutorial. So this is what you should be looking at in your second tab for the notebook aspect. All right. So in this notebook as a strong lensing demo, I've got sort of some of the same introductory information as before. And I wanted to make the note, sorry if this is a bit small, let me make it a bit bigger. Wanted to make the note that the term source has multiple meanings, because I know in the field of strong lensing, the term source refers very specifically to the background galaxy. But in the Rubin data products, and for most of this tutorial, the term source refers to a detection in a visit image, not necessarily the background galaxy. So that could get a little confusing, especially for the strong lensing experts that are here. Every time I say source, I just mean a detection in a visit image. All right, and like with the portal tutorial, this is not an introductory level tutorial. This is pretty intermediate advanced. And so if you're new to the Rubin Science platform, there are a bunch of other more introductory level tutorials that teach you how to use the butler, how to display images, how to use all of the tools that I'm going to use today are presented in a much more step-by-step way in our DP 0.2 documentation. You can find many more tutorials. But let's get started and have some fun. Let's do some lensing science. Start by importing all the packages that we're going to need today. Great. For image display, we're going to be using Firefly within the notebook aspect, which is essentially the same tool that you use in the portal. It's just used right next to your notebook here in the notebook aspect. Great. We're going to instantiate the data butler, which when you're in the notebook aspect, that's the way that you query for data, especially images, query and retrieve images. We're going to need this function to rotate an exposure. So execute that cell. I'll explain why we use that later. So the first step, we want to, since there's no strong lens sources in data preview 0, we want to get a stamp, a little image of a known lensed object. And for this tutorial, I'm using the cosmic horseshoe, very famous, easily recognizable shape. And I got an image from the DESI Legacy Imaging Surveys, the legacysurvey.org image viewer. So this is a little DECAM image of a known lens that we're going to take and put into LSST-like images and then practice detecting lensed objects. So that's what the little stamp looks like on its own. You can see the lens here, the foreground galaxy, and then the background source, the background galaxy that is strongly lensed. So we're going to take that and the first thing I want to do is make 4 versions that are rotated. So when I take these, we're going to inject them multiple times into an LSST image with like different locations and orientations. So just to make that part easier, I'm going to take this image and save it as 3 additional FITS files where it's rotated around so that we have just different examples. And that was very easy. What it's done is created a few more files over here. Should have created, there it is, there's the third one. Great. So now we've got a bunch of files ready. The next step is to use the data butler to get an LSST visit image to inject galaxies into. We could have a whole other tutorial on how you select images and find them in the butler, but for the purpose of today, all we did was to designate the visit number and the detector number and the band. And then we retrieve the CalX, which remember is the way we refer to single visit images from the butler. So there are many, many other tutorials that show how to use the butler, what is a visit, how to identify images, that kind of thing. But we're getting just one visit image and we can display it using Firefly here. It automatically displays with the mask plane on it for your extra information, but we can set that mask to transparent. So now we've got a process visit image and we've got it displayed. That's great. I'm going to want to inject a bunch of sources just into the central regions. So this next cell, all it's doing is getting the WCS from the CalX that I just got. It's getting the boundary boxes and then it's defining just like an area in the center where I'm going to use for all of the source injection. It'll become obvious what that means once we inject the sources and you see them. One really nice thing is that a tool for injecting sources into the CalX or in any image really already exists in the LSST science pipelines. It lets you just say like, I want to inject this many galaxies that are this size of this brightness with this kind of like orientation and this kind of shape. And it lets you just sort of set the parameters and then it will go off and inject 2-dimensional light profiles for whatever you define in there for you. This part, this section 4.1, not related to strong lensing, but it is related to using the source injection tool. So I thought I would keep it. So we're actually going to inject like 32 regular galaxies, regular elliptical galaxies, and then 32 versions of our rotated stamp so that you can just have like options and alternatives and learn how to use the injection tool. So the first thing we do is set up an injection catalog with a bunch of like elliptical galaxies, which you will see in a moment. And then we also add to this catalog 32 versions of our cosmic horseshoe stamp. that are at different RA. So we define the different RAs index. We want to scale them to magnitudes between 18 and 21 magnitudes and choose randomly between our four orientation options. So this is adding more rows to this injection catalog that define the parameters for our um, injected sources. And I think this will become clear once I show you this injection catalog is what we've just made. So we've got 32 objects with SERSIC profiles to the RA index that they'll be injected at, some of the parameters that define what shape and what brightness they're going to have. And then we also have 32 versions of our stamp that we're going to provide, all the RAs index for that stamp, the brightnesses that we want that stamp scaled to, and here you can see which file is being used, so the different rotations. So altogether, we've just created this list of 64 objects that we're going to inject. Half of them are galaxies that are normal, and then half of them are sources that are the cosmic horseshoe, just at different locations with different brightnesses and um, different rotations. The next step is to sort of set up this injection tool. And so we get the PSF, the photometric calibration from the visit image that we just got. There's whole other tutorials on how to use the injection tool. So we are just sort of doing the setup here for it. Why are there 131 objects in the injection catalog? There aren't. There's 0 to 31, and then I started the numbering for the stamps at 100. So it looks like there's 131 rows, but it's discontinuous in the middle, and the table length is actually 64. Good question. Good question, Nandini. Thank you. It's just the injection ID. I started at 100 for the stamps. Yeah. All right, so here we've prepared to do injection, and the injection task is going to take the catalog we just made and actually inject everything that we want into the image. This step does take a little bit of time because it's creating all these images and then putting them into the single visit image. So I think this took about a minute when I was testing earlier today. But let's see what it does now. Okay, good. So the injection has been done. This is just a simple little step to clone to make injected underscore calyx to be our image. So let's take a look at our image now with our sources injected. There they are. You can see there's a bunch of stuff. Oh, let's, yes, the mask. So you can see a bunch of galaxies, elliptical galaxies that we've injected have appeared. And then also a bunch of the cosmic horseshoe is in there as well. Let's mark them. So the cyan circles are all at the locations of normal galaxies, and then the orange circles are all at locations of injections of our cosmic horseshoe. Then if you zoom in, you can see that you've injected the cosmic horseshoe into this image. Can you remind me where to find the file cosmic horseshoe.fits? It should be right in there. If you git cloned the repo, it will be right in the same folder as the Python notebook that we're using. So if you only downloaded the notebook and you didn't git clone the full repo, you'll have to go back to where you got the notebook from and also download cosmic horseshoe.fits. But it is easier just to git clone the, yeah, that's why. Okay, yeah. All right, very nice. So that has worked. The next step is to run source detection. So now we've got this image and it's got the injected sources. The next bunch of steps also come from like an entire whole other tutorial about how to do source detection. But the next steps characterize the image, they detect sources in the image, they do the deblending, and then they do measurements on the detected sources. So learning how to do this is really not the point of today's tutorial. So I'm just gonna kind of zip through these sub steps where we're setting up the source detection task with basic configuration files. Just sort of zip through these sections and start running these steps. So you can kind of tell we're characterizing the image. We're running source detection on the image. We're doing deblending, run the deblend task on the image. Once deblending is done, you can go back and make measurements on the deblended objects. And exactly how you set the configuration files, how you set up the tasks, what all this means. This is quite technical and it's in other tutorials. Um, All right, so altogether we've detected 3,273 sources in our image that has the things injected. There's some options here to help you learn more about like what the sources is that you've just discovered, what are all the columns in this new source table, what all has been measured. That's all, you can uncomment and play around with these later. But let's just mark all the sources that we found. All the sources that were detected, mark them with a red circle. All right, this is all the sources we've detected. And right away, if you sort of zoom in on one of your orange circles, you can tell that the lens galaxy was detected and gets one red circle. And then the background galaxy has often been deblended, and so it gets detected as multiple children here. So there's multiple detections. So the single arc of a background strongly lensed source would appear as multiple sources in a source detection table. That's like the point that I'm trying to make. The next couple steps of the notebook tries to do like more investigation of the parents and the children. So a parent is when like a single blended object is detected all as one at first. That's the parent, and then it gets deblended into multiple children. So here, I just want to explore the number of parents and children. Altogether in our image, there were 225 objects that were detected that then had to be deblended. And then this is a histogram of the number of children per parent. So you can see that some parents were only deblended into two. That might be cases where there's two galaxies or two stars that are like close together, just chance alignment that they were deblended into two. And then the largest parents in this particular image were deblended into 31 individual child objects. So here I'm just trying to teach you a little bit about if the concept of deblending in parents and children is new, just trying to teach you a little bit about what that means because it is important for interpreting detections of strongly lensed objects because they do get deblended. All right, I've erased all the sources, all the markers on my image, and I want to mark only the injected stamps of the cosmic horseshoe in orange. All right, so just our injected stamps of the cosmic horseshoe. Now I want to mark only parent sources. And you can see that in some cases, if an object in orange also has a red, it means it is one of our injected cosmic horseshoe sources, and then the red means it was also a parent that had to be deblended. In some cases, we have an injected cosmic horseshoe like this one here. It's marked in orange, but it doesn't have a red circle, and that just means that it didn't have to be deblended, which basically means that only the lens galaxy was detected because this is a relatively um, faint injection here. So the background lens was never detected and never had to be deblended. So that's why it does not have a red circle, because it has no children. Did not need deblending. That's that point. Let's erase all the markers again. And now I want to explore which injected stamps are detected. And so here I'm adding a few columns to our original injection catalog that will hold the information about the detection of that particular injection. So I add those columns to my original inject cat table. And now I'm going to do some preparation for matching. So what I'm doing is for every injected object, I'm finding the detected source that best matches it. So I'm just doing like spatial matching between our injections and the sources that we detected so that we can say whether or not one of our injected sources was detected. That's what this cell does. It's going to do the matching. And then I want to show you now, we looked at inject cat before. And so what we've done is add 4 columns at the end. I only care about the stamps right now, so they're only populated for the injected stamps that we did. And it's got the pixel coordinates of the associated source that was detected in the image. And then it's got a bit of extra information like the source ID in our source catalog and the number of children. So that's whether or not if it's 0, then it didn't have children and didn't need deblending. But in some cases, you can see that on one of our stamps need a lot of deblending. So let's again mark only the injected cosmic horseshoes in orange. And now let's add red markers, where this time the size of the red marker corresponds to how many children the source had in our source detection. So it's like the same size or just a little bit bigger than the orange marker. It had no deblended children, and this one has like a really big circle. So it had a lot of deblended children. But what we really want is to also mark just the children on there. And so we can zoom in, for example, and see in this case for very bright, this one was pretty bright that we injected the cosmic horseshoe. And so it was detected, and it's the arc there was deblended into many children. There's another example, and an example of one that didn't need deblending at all because the background lens galaxy wasn't detected. So all of this is just trying to give you a sense of how lensed background galaxies end up in the source catalog as deblended children. The very last step of this notebook just goes through these deblended children and looks at the flux and the shape, basically. So I'm using ellipticity as the shape of these individual child detections of the arc. And it just gets them all. And then the actual point here is a plot of the ellipticity measurement for sources versus the brightness, the log of the flux, where the gray points are all just sort of like normal galaxies at real sources in the image. And you can see the gray points follow, a trend in the image. And then the only point I'm making here is that the children of the cosmic horseshoe, which is the individual sources that are detected, they have just a different pattern in shape versus flux because they are all have all been lensed. So this is like a very just sort of rudimentary demonstration that when you're going into the real data and looking for lensed objects, you might be able to use some of the shape measurements that we already have to sort of identify things with an odd shape, things that have different shapes, different ellipticity versus flux, values than normal galaxies or than the rest of them. So this is just sort of an example of how to use shape measurements that are already in the catalog to explore potential lensed objects. Is there documentation about how the deblending algorithm works? Yes, it's the Scarlet deblender, and I think there are papers out there already on it. And then there will be definitely algorithm papers that come out with Data Preview 1 that describe in a lot more detail how the deblending algorithm works. Yeah, that's a good question. All right, so that was the goal, was just to have you touch data via the portal, touch some data via the notebook aspect, and to yeah, to sort of get in there and visualize what lens sources might look like in Rubin data. So yeah, and we have 5 minutes left for other questions and issues. I'll start with the Zoom. Is the proximity matcher essentially running same code as association? No, I don't think so. In this case, it's just um, when I do the matching, wherever that was, very, very basic for the purposes of the demo. Um, it's kind of described here. This is not any sort of like real or official code from Rubin Observatory. It's just me going in and saying, oh, that's probably that one, that's probably that one. Um, Source association is something else. That's not what we're doing here, not formally. Other questions? All right, I'm gonna stop recording.